You know, when Isaac Newton came up with physics, one of the very first things that he concerned himself with was trying to understand motion. And he tried to get a handle on this quantity that we know of as motion. He called it the quantity of motion. We now call this same thing momentum. And it's more than just about the velocity of an object. Whether or not I get hit by a table tennis ball moving at 40 miles an hour, or whether or not I get hit by a bus at 40 miles an hour, well, the momentum is going to make a very big difference to the situation. So we need to get a handle on this quantity to understand what it is, what makes it larger or smaller, and how it is involved in other physics and in situations that we might observe in our daily lives. What I have here is a ballistic pendulum that I've taken apart just so I can show you. It's got a really cool ball firing mechanism just here, a little cannon. And what I have here is some oasis. It's the sort of thing that you would use to stick flowers in a flower display. And what I'm going to do is I'm going to fire the ball into the oasis and have the ball hit the oasis. And I'm going to observe the effect of the different speeds. You see, the more I pull this back, the faster I can make the ball fly out, and we'll observe the effect of different speeds hitting the oasis. Same ball, different speeds. Come closer. That was so exciting. When I fired it at really low velocity, it made just a little tiny impact into the oasis. And when I fired it at a much larger velocity, you can see it's gone so far into the oasis, I can barely touch the ball bearing anymore. The more speed it had, the more impact it had when it hit this. Now I'm going to say that that is due to momentum. But the velocity of the ball is not the only thing that is going to affect how this behaves when it's hit, because I think that how much mass the projectile is carrying also makes a difference too. So let's investigate that. I want to change the mass and see the effect on the oasis. So what I have here is I have got two different things. They're identical in their size to each other. This one, let's put it on the scales there. Look at that, 1,000 grams. It is in fact a kilogram. And let's have a look at this hefty beast. Let's put it on there, 8 grams. That is because this is made out of foam. Let's see the effect when we drop them both from the same height onto the oasis. And what that's going to do is it's going to control the speed at which they impact. You see, falling from 1 meter is going to have the effect of, because objects fall at an acceleration of about 9.8 meters per second squared. They're both going to hit the ground at the same speed, and so it has controlled the variable of speed. And what we can see is the effect on the oasis caused by the collision with the mass. Now I'm going to make a prediction, and that is that the heavier object is going to hit harder. Now there is nothing more fun than this, so I suggest that if there's any way you can go do this experiment, just go do it. Let's do it. That was just awesome. So this 7-gram version of the kilogram mass landed, didn't even leave a mark. And yet the 1 kilogram, oh, look at that, a perfect cast of the mass. So what is really clear in terms of the impact on something like this is that 2 things are involved in the motion of an object. There's the velocity at which the object is travelling, and then there's the mass. Now these two things together count. If I doubled the velocity and doubled the mass, the object would hit 4 times harder than before. Now this means that this property of motion must be found by multiplying the mass and the velocity together. And we call this quantity momentum. The quantity of momentum here are the facts. To start with, what kind of quantity is it? Well, it's a vector quantity. And that basically means that it can have positive or negative values depending on the direction that the object is moving. If it is moving in the direction you've described as positive, and it has a positive velocity, it's going to have a positive momentum. If it's moving in the opposite direction, in the direction that you have defined as being negative, its velocity being negative, then the momentum is going to be negative. Momentum is given by the symbol lowercase p. And its units, well, its units come from the equation. The equation for momentum is that momentum is equal to the mass times by the velocity. If the units of mass are kilograms and the unit of velocity are meters per second, then the units of momentum are going to be kilograms meters per second. So the units, kilograms meters per seconds. Now before we get any further with our understanding of momentum, we need to be really clear, because there are two completely separate situations where momentum is involved, but they're very different from each other. We have this here. We call this an open system. And we know it's an open system because there is an exchange of energy with the outside environment. And this is in the form of external forces doing work on the car, in this case, friction. Woo! Okay, not a lot of friction, but definitely some. In this situation, the momentum of the car went down. This is because kinetic energy is being lost, and as a result its velocity is decreasing. All of these things are connected. But it is because external forces, friction, are making it happen. This is a special situation, and we'll talk more about open systems later. But what if we could get rid of the friction? Would something just keep moving forever and ever? Well, Newton's first law suggests that an object at rest stays at rest, and an object moving at constant velocity stays at that velocity until an external force acts upon it. However, that's very difficult to do in the laboratory because there's always external forces. There's always friction, air resistance, etc. But we have devised a way of getting rid of most of those forces so we can see the physics of a closed system. A system where there is no energy being lost out of the situation. And we do it in physics with this big piece of apparatus. It's called an air track. It's very like the technology used in an air hockey table. What it is, it's a big tube with holes in it, and air blows in one end. It's wonderfully noisy, but what it does is, as the air blows out, it takes this small car here, and it basically makes it hover. So there's no friction between the car and the track. And this means, when I set this into motion, it should continue in motion, at least for a very long time. Let's give it a go. Okay, so the air track is on. It's not quite balanced. You can see the car is moving, so we'll try and balance it so that it stops doing that. What you can see, if I set this into motion, it will just continue in motion for a really long time. Oh, until it hits the end. And this is what we need for a closed system. But here's an extra detail. Come on in close. My object moving at constant velocity would continue to do so forever. But that's not to say that the velocity cannot change, because it could change if it impacted upon another object in that closed system. Here we have a closed system with one object in it. By adding a second car, I can make a closed system with two objects. And of course, what's now going to happen, if I set this going, is they're going to interact with each other. But neither of them are being acted upon by forces from the environment. So let's give it a little go and see what happens. We turn on. If I bounce this one into this one, you see there is this interaction between them and all sorts of things occur. With a small amount of modification, I can make this air track the apparatus that enables us to measure the momentum. So what two quantities do I need to measure for the momentum? Well, it is the mass and the velocity. So if this is my object, well, I can measure the mass by putting it on a laboratory balance. I find that it is 204 grams. Now on here, the other piece of information I would need to measure to calculate the momentum is the velocity of the object when it's moving. So what I've got is a light gate here connected to a data logger, and there's an interrupt card on the top of this object. When I turn the gas on, and when I turn the data logger on, it should then record the velocity of the car. Let's give it a go. So we turn that on, and we turn the air track on, and off we go. Excellent. It went through at 1 metre per second. So if this was 204 grams and this was 1 metre per second, then the momentum is going to be 1 times 0.204, which means the momentum of this was 0.204 kilograms meters per second. But this apparatus is really versatile. One of the things that we can do is we can add a second light gate over here. One light gate there, another light gate over here, and actually have them both feed data to the data logger. And that means that we can measure the velocity of more than one object. I know. So here is the first trolley over there. This light gate will measure its velocity, and this trolley over here will have its velocity measured by this light gate. So what we can start to do is look at what is going on in more complex situations. Let's give this a little go. Press play on the data logger, run over here and we turn on this. And what I'm going to do is I'm going to send these at each other. 3, 2, 1, and off they go. Wow, look at that. We got the one on the left was going at 0.7, the one on the right was going at 0.6. Amazing. You might have noticed something there. What happened was that the cars went through the two light gates and it recorded, quite rightly, the velocity of the car going through that light gate and the velocity of the car going through this light gate. But what happened next was that the two cars bounced off each other and then flew backwards through the light gates. It didn't actually record the reverse passage, but what has happened is there was a situation before the bounce when they were both moving inwards, and there was a situation after the bounce when they were both moving outwards. So for any one of these objects, we could measure the velocity that it had before the collision and the velocity of the object after the collision. So that's two possible velocities we could measure for that card and two possible velocities that we measure for that. The key thing is, when the collision occurs, this event changes things.
it changes the distribution of momentum between these two. But it leads us to a glorious idea, an idea that we can prove with this apparatus. And that is that even though the momentum of that cart will change, and the momentum of this cart will change, the total momentum that they have together will remain the same. However much they started with is how much they finish with together. We call this idea the conservation of momentum. The momentum can neither be created nor destroyed, it is just simply redistributed amongst the objects involved in a closed system.
So let's do it! Right? Here we can actually see if conservation of momentum is a real thing or not. What I've got now, I've got two cars. This one is between the two light gates. This car here I'm just going to push through. I'm just going to go through here and measure velocity here of this car, and that car is going to stay stationary to start with. So all of the momentum in the system before the collision is going to be carried by this car. It's going to strike that car, and that car is going to go through that light gate, and we can then measure how much momentum the situation has afterwards. So we need to record some things. First thing, most importantly, we need to get the masses of these two cars. So this is where good record keeping is really important. Okay, we'll call that car A, and its mass is, well, it was the same one as we had before, so its mass is 0.204 kilograms. Good job, car A. And now let's get car B. And car B has a mass of slightly more, 0.205 kilograms. They are very, very closely balanced. I wonder if I can make it exactly now when you try. Okay, so that's that. The next thing I need to do is to record so before the collision, I need the velocity of car A and the velocity of car B, and after the collision, I need the velocity of car A and the velocity of car B. So each car, I need to know how fast it's moving before it had the collision and after the collision. So I'm saying that this one's going to be stationary to start with, so that's something I can already put in. But this one is going to go flying through. Now I might have to jump in and actually stop the movement of the cars so they don't just keep going forever. All right? I think we're about ready. So let's press play on this to see what happens. And let's turn on the air. And we turn it off, and we're going to have a little look at what those velocities were. So, before, the velocity of this one was equal to 1.17 meters per second. Afterwards, the velocity of A was 1.11 meters per second. The velocity of B was then stationary. I've got my data. Let's have a little look if it works out. We have our data. Let's do some calculations. So we need to talk about what happens before the collision and after the collision. We need to know, we called it car A and B, didn't we? What was going on with car A and car B? And we want to know about what the total is when we're calculating the momentum. So remember, the formula that we are using again and again and again today is that the momentum equals mass times velocity. So before, car A has a mass of 0.204, and its velocity for car A is 0, which means car A has a momentum of 0 kilograms meters per second. Car B has a mass of 0.205, and it has a velocity of 1.17, giving it a total momentum. So that's 0.205 times 1.17, a total momentum of 0.24. 0.24 kilograms meters per second. 0 plus 0.24 gives a total momentum of 0.24 kilograms meters per second. So that is the total amount of momentum in the system between the two cars before the collision occurred. But what about after the collision occurred? Let's have a look. So car A afterwards, the mass was the same, 0.204 times the velocity of 1.11, so 0.204 times 1.11 is 0.22. 0.23, rounding up, kilograms meters per second. The second car, car B, was 0.205 times, and it was not moving afterwards, so that is 0 kilograms meters per second, which means that the momentum was 0.23 kilograms meters a second. What do we notice? That they're approximately the same. Experimental uncertainties, maybe that the car B maybe wasn't completely stopped, maybe my ramp wasn't entirely level, who knows? That's what's caused the ever so slight difference, but the key takeaway fact is that the total amount of momentum that the cars had before is how much momentum they had afterwards. Let's look at that play out in slightly different circumstances. In that previous example, what happened was the two cars engaged in a collision and then both sprung apart again. Now, what we had there was two initial motions, though one of them was stationary, and then afterwards there were two separate motions because the cars were off on their separate ways. But there's a second type of situation that I want to bring to your attention, and that is when the cars do not spring apart, but end up merged together, coupled by some kind of mechanism. Now, what I've done is I've changed the setup of the experiment this time, and there's a rather lethal looking pin on the end of this car. And here, adjacent, is a cork. When I slide this car at that car, they should then stick together and move as a conjoined object. Now, if we're right, conservation of momentum should also apply to this situation. So let's give it a go. Right, now a key difference here is that we need to understand that car A is sliding towards car B, and then the collision occurs and car A and car B are now merged together, and that's an important thing we need to remember. So for car A, its mass was 0.204 and it was moving with a velocity of about 1 meter per second. So the momentum of car A to start with, 0.204 times 1 is 0.204, I don't know why I'm doing that on the calculator, is 0.204 kilograms meters per second. Car B, also 0.204, is moving at 0 meters a second because it's stationary. And so it has a momentum of 0. So the total momentum of the system before the collision is equal to about 0.204 kilograms meters per second. Now, afterwards, what has happened? Well, what we find is that we now have the combined mass of 0.204
added to another 0.204, which gives 0.408 as the mass, 0.408 kilograms. Now, what you can see here is we recorded a velocity of 0.42. So that's the mass, the velocity is 0.42. So what was the momentum of the total situation afterwards? So let's do it. 0.408 times 0.42. 0.42. And the answer is about 0.17 kilograms meters per second. Now what you can see is that the momentum before is approximately equal to the momentum afterwards. The momentum has been conserved even though the cars have stuck together. But what's really curious, considering the fact that both of these cars are the same mass as each other, is that when the car by itself came hurtling in at this velocity and it hit another car and then combined, the mass doubled. And so the velocity halved. And this was so that the momentum could be the same before and afterwards. Both of those last two examples were collisions, that the two cars came together, impacted, and then something else happened afterwards. But conservation of momentum is also useful as a technique for situations that we describe as explosions. Now, I can turn this collision into an explosion by doing one thing. If I turn these two cars around, you'll notice that they both have on them elastic bands. And what happens when these get pushed together is the elastic bands press on each other and it forces the two cars apart. So what I'm going to do is I'm going to turn the air on and then I'm going to squeeze these two together and let them go. And this is going to be an explosion. So here comes the air. I'm going to press play on my timers. I'm going to squeeze them together like this, and 3, 2, 1, let go, and there they go. So we'll just stop it there. And now, what happened there, after they were let go, is that they both moved apart. They're both equal in mass, and what we can see from the velocities is that they've both moved apart. This one with the same velocity in this direction as that one had in that direction. What is going on in an explosion? Where has this motion come from? Well, being a closed system, momentum has not been created or destroyed. And to start with, there was zero momentum because both objects were stationary. But if you think that this one has carried away some positive momentum, its mass, 0.204 kilograms, multiplied by, in this case, 0.3, this one over here has carried away the negative amount of momentum that would have been the same. So this one has got a same mass of 0.204, but has passed through this ligate at minus 0.35. The positive momentum carried away by this is equal to the negative momentum carried away by that, so that the combined total momentum is still equal to 0. Now this leads to a very interesting effect. An explosion is an example of conservation of momentum. To start with, there is zero momentum in this system, and then when triggered, both objects move away with equal and opposite momentum to each other. The positive momentum carried off by that cart cancels out the negative momentum carried away by that cart. It still equals 0. But what happens when we change the masses of the two objects and we make one much heavier than the other? So now we're running it again, but we've put 5 kilograms on one of the cars and we've left the other one empty. Watch the difference that this makes. What happened was that this one has barely moved and that one has gone away almost 5 times faster. This is the situation that occurs when a gun is fired. To start with, the bullet and the gun have zero momentum. Then there is an explosion and the bullet comes out of the barrel. But because the bullet is so much lighter than the gun, the bullet proportionally moves so much faster so that it has the same momentum going forwards as the heavier gun has going backwards. This is called recoil. All of those examples that we've done so far are closed systems, the interaction of two objects in a collision or an explosion. But what we also must look at is what happens in open systems, when external forces acting on the object will slowly decrease the momentum. Well, this is an example of an open system that we've set up here. It's an inclined plane and we're going to roll a car down the thing. It's got a kilogram mass on it for extra effect. And to demonstrate what happens when this hits an object, I've got this oasis just here. And the two things we're going to do, the first time we're going to roll it down and it's going to hit the oasis with the extending spring out the front locked in place. So there's no give in this whatsoever. The second time we will do it with it not locked in place and there is a certain amount of give in the spring. Look at the difference that that makes. Wow, look at this. When the spring was locked out, it has penetrated 2 or 3 centimetres into the oasis. When the spring was not locked out and there was a give in the system, it only went in about 3 or 4 millimetres. So there was something about having the spring able to go inwards that actually reduced the amount of impact on this oasis. We can go beyond playing with oasis. We can actually take some data. And what we have here is a force meter. This device here is going to electronically measure the amount of force it experiences when it is hit by the trolley. So if we repeat the experiment, this time, is it locked or is it on the spring?
This one's locked.
So this time it's locked, we're going to send the car and we're going to see how much force is measured at the pole at the end.
It's 19.5.
Minus 19.5. So what is it when we turn the spring on?
Minus 16.2.
So when there was the spring, there was significantly less force applied to the force meter than when it just hit without the spring. So there was something about having the spring cushioning the blow that reduced the force. Well, that makes sense. But is there a way of linking this to our understanding of momentum? Of course, what is happening as this car accelerates is it's gaining momentum. And here it has a whole load of momentum. When it collides with an object, that momentum is changing. That momentum is changing to 0. And so there is a momentum change going on. Now in physics, we call that momentum change an impulse. And what matters as much as the size of that momentum change is the time interval over which that change is occurring. So in this instance, when there was no spring, that momentum change was happening in a very short time interval, almost instantaneously. But when the spring was engaged, there was a much larger time interval as the spring scrunched up, over which that momentum could change, and that had a massive effect on the crash forces. The more rapid the change in the momentum, the higher the crash forces. Do you remember when we spoke about acceleration? Well, we use a formula. A is equal to v minus u over t. And this was to represent the difference in the velocity between the initial velocity u and the final velocity v. And we give it two different symbols just so that we know which one we're talking about. U comes before v in the alphabet, so u is initial and v is final. Now we can use those symbols to talk about momentum as well. Now of course the symbol for momentum is p, but we could just write out the formula for momentum, mass times velocity, and that would also represent the momentum. But which velocity? If our velocity is changing, as indeed it seems to be in this experiment, then we could talk about the initial momentum, which would be mu, and the final momentum, which would be mv. And if we wanted to know what the difference was in those momentums, we just have to take one away from the other, just as finding the difference in these velocities requires us to take one away from the other. We can in fact work out that the difference in momentum is mv minus mu. Now this is the momentum change. But what was relevant in the experiment that we just saw was not just how much the momentum had changed, but in the time interval over which that change had occurred. So we need to find out what momentum change has occurred in a given amount of time. Now this is what we know of as the quantity of the force. In our situation, it was the crash force of the vehicle. When the momentum change is large, the crash force is large. So if you crash from high speed, there's going to be large crash forces acting on you. But because this is divided by time, it means that the force and the time are inversely proportional. It means that if the time interval is small, then the force turns out to be really big. If the crash interval is larger, then the force will be less. So to reduce the braking force, one thing we could do is change our momentum over a longer period of time. Increasing that time interval over which the momentum changes is a way of making sure that crashes become survivable in cars. There's a number of safety features that allow that to happen, including the crumple zone at the front of the car, which will decrease that momentum over a longer period of time. As well as the crumple zone, there's also the airbag. In a collision, the airbag would inflate, fill this space, and it would bring my head to a slow, gradual stop over a long period of time, reducing the crash forces on me. And finally, the seat belt. This has two parts. The lap belt keeps you in your seat, but this brings you to a stop over a longer period of time, all of which make a crash more survivable, and this is through a knowledge of physics.